And what is the ratio of expansion in this direction versus the expansion? Does everybody understand that? That for this structure, it's actually called expanding sphere. It's expanding in this direction, and it is expanding in this direction as well. You see that? Okay. What will be the Poisson's ratio of this structure? What is it? You have to give me an answer. Is it really 1? Look at the definition. -1, -1. Why? They expand the same opposite too. Okay, so I'm going to pass them around together so that it, it's very easy for a human to get things backwards. I'm trying to understand why AI can, when it generates an image, it can take a person and can put the upper body at 180 degrees, like an owl. And I think there's something to do philosophically with what just happened here. So the answer is -1. And majority of the materials have Poisson's ratio of 0.25 to 0.5. And that's what you need to remember. So don't let this stuff confuse you. I just brought it for educational purposes so that you kind of like get an idea that for every law there's an exception. Or for every definition there's an exception. What I'm passing around is called functionalized Teflon. And the reason it does this, by the way, sponges do the same thing. They can have either positive or negative Poisson's ratio, depending on the arrangement of the cells in the sponge. Okay? And the maximum value of the Poisson's ratio for homogeneous material is Joby, Joba, da 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 da. I went to a concert. I went to the Gypsy Kings concert. Do you know this song? What's another popular song that they have? Bamboleo, Bambolea. Do you know that these guys are actually French? Or they're from part of the France that speaks Spanish? Do you know that? And the lead singer is old. I'm trying to convey the knowledge, and I'm providing you with free entertainment as well. I'm not as good as those singers, and I'm not charging the money directly for the tickets. What is the maximum value of the Poisson's ratio? 0.5. Yes. 0.5. Please remember that. Now that thing is -1. And that Teflon, who knows, probably also like minus something, but those are exceptions. You just need to remember that for most of the materials, it's like from 1/4 to 0.5. And when every material deforms plastically, what is the Poisson's ratio of material that deforms plastically? It goes to the maximum value of 0.5. So even though you have steel that has Poisson's ratio of 0.25 or 0.3, depending on what it is, you can look it up in a table. Whenever that steel starts to deform plastically, it's 0.5. How do I know that? By spending $300,000 of our money in a research project, NSF sponsored. Something that the book doesn't tell you this explicitly. Anyway, the other thing that I brought today is related to the stencil machine. In fact, here. This is the tensile machine, and you see here on the top it says load cell. What is a load cell? And what does it do? Yes? It measures the load. The load is applied by a, see, there are two screws here, and once they start turning, like in a vise, this crosshead, it's a moving crosshead, it moves up or down, okay? And then there's a load cell, and it's electronic. So whenever you go to Publix to buy apples, or whatever you buy that they need to weigh, they put it on the scale, and they tell you how much you're supposed to pay. How do they do that? What? Yeah, how does it work? Yeah. It measures the force of how? Spring constant. Okay, so what you see here is the load cell. And I want you, and this is a mechanical one, I picked it up off of eBay for cheap. But you can see that this is actually a micrometer, okay? And this micrometer has, I can move it. And what they've done is they've taken this part, which is not manufactured by the same company, but they manufactured this, and there's a way to fix it, and you can see that when I'm applying the force, it's measuring that, okay? It's measuring that using the Hooke's law. By having known the spring constant of this. I'm going to calibrate it. I want you to look how much it sells for. The cell is in series with a sample. And it's measuring the load. Now the displacement is measured by this extensometer or sometimes by this crosshead. What we were doing with the student just before this is I built a tensile machine. A portable tensile machine for measuring elastic properties of like thin wires. Oh my God. Shoot. Elastic biomaterials. It can study whatever properties, but the machine looks like this. It's portable. That machine that I showed you starts at $50,000. You know, the big one, and it's stationary. I could have brought it here. It comes in a suitcase, which says Dexter on it. It does say Dexter. But this is what's inside. All right, there's a stepper motor here, and this is the circuitry that connects to a computer through a USB to COM port adapter. Here's the power supply, and basically you just, the sample fits here, like this, a thin wire. And all of this is flimsy, so when the paperwork was reviewed, they said, what are you doing? You're like, this is very flimsy. So the one that actually is working now is much more rigid rather than this. But the idea is that you can get the load versus displacement curve, and some of it is for this super elastic material, some of it is for human hair and skin and things like that. This is to rupture. Okay. Now we discussed elastic properties, which is the ratio between the stress and strain, proportionality constant using Hooke's law. The same principle that this load cell that I'm passing around is also using the Hooke's law. It's using the spring constant of this device to measure the load. But it's actually measuring displacement. And you can see that very well in that specific device, which is why I bought it, so that I can show it to students. So you understand, like, the simple concepts. They're simple to me. Doesn't necessarily mean that I can transfer the knowledge. I wish in our day and age, you like that? Yeah. $5 at the Discovery Channel store. 10 years, 20, 30, 20 years ago. I don't know how much it is now. Maybe cheaper because you can buy it off of Amazon.
And this coming, I don't know.
Okay. What is determining the elastic properties of material? What is happening at the atomistic scale when we are applying external forces to it? Yes? Okay, we're creating more space between them. Sounds like the beginning of a good song. But it's true, but it's elastic, meaning that those atoms, physically, they don't move. But the bonding between those atoms, that's what gives that resistance, right? And how can you change the elastic modulus of a material? Yes? And then what? So the stiffness, what you're implying, I assume, changes with temperature. Okay. Case hardening. And then what? And then what? And then that's only 4 millimeter layer, right? And does that affect the gear that's this big? The reason I'm asking you is that if you have this material, there's really no way to change its elastic modulus. We will talk about alloying. So when you like take 50% copper, 50% nickel, and you make an alloy, then the alloy elastic modulus would be different than nickel or aluminum. But once I give you a chunk of metal, and we're at room temperature, it doesn't change that much. Okay? What is this class about? To control the process, to control the structure, to control the properties in that order, because there's a cause and there's an effect. Okay? Bam! This is the process. Ooh, something happens with the material. And then we're testing the properties. Okay? That's to control the process, to control the structure, to control the properties. Elastic modulus, we cannot change much. But what I want to show you is this graph here that shows the yield strength when we discussed plastic deformation. Here. You see what it says here? Room temperature values. Room temperature values. And what we can really change is the yield strength. So going back to $300,000 salary that you're getting after you pass this class. We take the same piece of metal, we put it in the furnace, and we take it out. And one we put in ice water, another one we let cool in air, and another one we put in oil. And the difference between the one that was in the ice water and the one that was cooled in air is a factor of 3. That's the yield strength. So plastic deformation happens by the generation and motion of dislocations. And once there's a traffic jam, they can no longer move. And we can change this quite a bit. In fact, we can make material that was ductile, like acting like silly putty, and we can make it brittle. Virtual material science, there's a module on tensile testing for different materials. Let's discuss what happens when we are taking the material and we're stressing it. So in that tensile machine that I showed you. So we apply the load. The load is applied either, there are two types. There's mechanical So there's a motor that moves the screw, or it could be hydraulic. So there's hydraulics that moves this and applies the external force, so you're doing this. And what happens initially, we're following the loading slope, which the proportionality constant is the elastic modulus. And then at a certain point, the material starts to deform plastically, which happens at 0.2% offset. So we come here at 0.2%, which is 0.0002. Just remember, 0.2%. 0.2% is easy to remember. Otherwise, there are way too many zeros and you can't remember it. 0.2%. 0.2% offset. We come down here and we follow the same loading slope, and whenever there's intercept with the data, that gives us the yield strength. Tensile strength is the maximum on that stress strain curve, and past that the stress continues to go down because this is engineering stress. And as you can see, due to the Poisson's effect, when we're stretching it, the cross-sectional area is reducing, but we're not taking that into account. So what happens in ductile materials, there's necking that happens, and the plastic deformation happens by, plastic deformation only happens by, you like that? Plastic deformation only happens by bamboleo, by shear. Plastic deformation only happens by shear. Why? What is shear causing? Shear is causing dislocations. And to cause the dislocations, you need to have shear. So how come when we're doing tension, there's shear? Well, half of you are in the other class that I teach after this one called Mechanics of Materials. The reason there's shear when you're doing this is because a force has a projection on a plane, right? So if I take a plane that is at 45 degrees like this, then this force is going to have a projection in that plane. And that is the projection of that force that is causing shear on 45-degree planes. It takes a whole class to explain that. Yes, sir? Regular. What's regular? Yes, there will be shear right away. And I tell you why. The shear will be on the plane, some arbitrary planes that are inside this material. Because this force in this vertical direction all of a sudden has a projection onto this plane. And it's in that plane. And if it is in that plane, that's shear. Yes. Yes, in the direction of stretching there is no shear, you're right. Yes, you're right. But I'm sorry, maybe there's a reason why there's a whole lot of the class that explains that, but just take it for granted. I'm just telling you. So this necking happens due to shear, and eventually it breaks this neck. The only reason it happens is we're going to discuss it. So the ductility is the measure of amount of plastic deformation in the material. There are two ways to measure it. One is in terms of the length of the sample when it fractured. Another one is in terms of the cross-sectional area when it fractured. So in terms of percent elongation, we take the length at failure. We take two pieces together. We stick them like this, and we measure the length. And we divide it by the original length times 100% to get a percentage. The other way is we are taking the percent of the reduction of area because it necked, right? So that area reduced in the neck region, and then we measure that and compare it to the original area. So this is A0, this is AF. You see it started to neck. This necking only happens by shear, which now you see a demonstration how one type of loading, which is uniaxial tension, is causing shear on the planes that are not aligned with the axis of the applied load. Any plane is going to have the projection of the force, and that's going to cause shear. Any questions about this? So here is a sample that has higher or lower elastic modulus than this one, than the green one. Which material has higher elastic modulus, this blue or the green? Has higher elastic modulus. Why? Great. What does have the elastic modulus to do with ductility? Yes. Don't mix American dollars and US pesos. I mean, you know what I mean. Apples and oranges. Okay? I mean, elastic deformation is elastic deformation, and the measure of elastic deformation is, it's the stiffness of the material, it's the elastic modulus. And the measure of ductility, it's plastic deformation, it's permanent deformation. There are several ways to measure it. One is the yield strength. So this material yield strength is here, and this material the yield strength is here, and this material has higher elastic modulus than this one because this slope is steeper than this. Okay? The yield strength of this material is also higher than this one, like here versus here, roughly. But this one has a lot of ductility. What does this mean? It means that you can stretch it to a very, very large degree of deformation. And because we, as process engineers, can control how much ductility is there by heat treatment, you want things to be soft when you're making it into the material, and then you want it to be hard when it is in service. But there's always a trade-off between ductility and brittleness. Okay. There's another property which is called resilience, which is the ability of the material to absorb energy during elastic deformation. And this is our 0.2% offset right here. If we unload from the yield point, it's going to follow this dashed line. And the area under the stress strain curve is equal to the integral from 0 to epsilon y sigma d epsilon. And then if we assume that the stress is proportional to strain, we're just taking an area of this triangle, which is equal to 1/2 sigma yield strength to epsilon yield, which is the strain at yield. And this is pretty much ignored because it's kind of like right there. Okay, so this is called resilience. Another parameter is called toughness, and it is the energy that is absorbed in the material before fracture. And toughness is an area under the whole stress strain curve to failure. We take this whole curve and we integrate it. And then you can see that if we take some polymer, it has small toughness. If we take a metal, it has large toughness. And for ceramics, it has small toughness, even though, you know, you're comparing this to that. So the elastic modulus of plastics is like several gigapascals. Ceramics is in the hundreds of gigapascals. But because it breaks in the brittle fashion, and this is stretched to a very large strain, then they're kind of like both small. You can see by how much I can stretch it. All right, this brings us to a very, 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 very important concept that's very often is ignored because it doesn't have a lot of practical applications. There's a difference between engineering stress and strain and true stress and strain. So, what is the engineering stress? When we take the load and we divide it by A0, and A0 is original cross-sectional area before we even started deformation. But even what you see now, because of the Poisson's effect, the cross-sectional area is reducing as we're stretching it. Okay? And this becomes even more important past certain events, especially if there's necking. And we assume that the curve looks like this and it goes down, the stress goes down. The stress actually doesn't go down because we're not calculating it correctly. That is why it's called engineering stress and strain. And it goes back to the Second World War and pre-Second World War. Analog world, which was not that long ago. That tensile machine outputs two parameters. It gives you the load on the sample, and it gives you the displacement on the sample. And that was recorded by an analog chart recorder. So there was electrical.
Sorry, mechanical.
You okay?
Yeah.
Okay.
Sorry.
No problem. There goes a $2,000 now. Maybe not. Okay. All right. True stress versus engineering stress and strain. For true stress, it actually continues to go down as the strain is increased. And there are two formulas that, by definition, is the load divided by instantaneous cross-sectional area. But you know, there was no video back in the day. Movies, but it was very expensive. Wow. Measure the cross-sectional area during the test. Because it was a pain in the ass. It still is now. I don't think anybody did anything like this. I want to do something like this, but I need another $300,000 from National Science Foundation. So maybe I'll write a proposal and use this machine with see, if you want to test something really basic, like, people don't give you money. You say, oh, we already know it. It's in the textbooks. But is it really like that? I mean, I can tell you for sure that nobody in the world ever measured the Poisson ratio of that functionalized Teflon. Google it. Poisson's ratio functionalized Teflon. See if you can find anything. Okay, but what's important is that we have conversion equations. And if we get the engineering stress strain curve, this one, it can be converted to this using these two formulas. So true stress is equal to the stress we calculate times 1 plus epsilon, and the true strain is equal to the natural log of 1 plus epsilon. So this problem is solved mathematically. And I've never verified if it's true. I want to, but it is in the textbook, so it must be correct. Bamboleo. Now, what is happening with the true real material is that it strain hardens. In other words, if we take elastic, perfectly plastic material, then it behaves like this. So we hit the plastic deformation, and then the curve is flat. And there's no slope to it. But the actual data shows something like this. This is actual data. Or some copper alloy. You see, for some materials, it's not a bad approximation. Plastic, perfectly plastic. So this curve is flat, but it's tested at 900. It's tested at 750. You can see there's some slope. And then if you look at this sample, so basically this data looks like this, and it's an approximation. So first we have slope that's related to elastic deformation and elastic modulus, and then we have strain hardening. So the equation is like this: epsilon to the power of n. And this n is called strain hardening exponent. It can be measured experimentally. What is the practical application? Practical application is very important. And if you take a paper clip and you start bending it, and you're super sensitive and you know what you're trying to sense from your finger, you would realize that the second time you're bending it, it's kind of a little harder. So the first time we take it to the point D, first time it yielded here. You see that? The second time it goes up to the point D. Is there a difference between this and that? Yes. So this means that repeated cyclic plastic deformation hardens the material. How did the humans use it centuries ago? Have you ever been to the Renaissance Festival? What's there? Blacksmithing. You can even see people fight with wooden swords. You ever see real swords? In Europe you do. I mean, they don't. Because this is a dangerous weapon. But how did they make those swords? And why are they so unbreakable? Blacksmithing. And the blacksmithing was to heat it up and hammer it, heat it up and hammer it, heat it up and hammer it. They didn't understand what they were doing. They empirically just knew how to cook the sword. And then you come to a cooking class here where I will explain to you how it's done, to control the process, control the structure, to control the properties. Okay, so first time it goes to sigma y0, second time it goes to sigma yi. I materials. And then you can load it the third time. It will go higher. But not all of the materials strain harden. All right, another measure of plastic deformation is hardness. And the way hardness works is you take something small and you indent it into the surface. And there are different scales which are very confusing. But I'm going to break it down for you. You take a material that's either hard steel or diamond or tungsten carbide or something that is hard, and you make an indentation. If I see, this is not real wood, this is a laminate. It's not so easy to indent. I mean, I can take a key from my office and I can scratch this board and destroy USF property. Let's do it. Trying to see something that's not gonna get me in too much trouble. Maybe this chair here. See that? I can feel it. It's an old chair. It's cracked. So. How did I do it? With my key. I could also take this key and apply the load and load it up with weights, right? And make an indentation. Permanent deformation. Okay? So let me give you a true definition of hardness. It is the load that was applied, like I can put weights, divided by the area of contact. You see, I made this, it's not a hole, but I didn't scratch it. I indented it. You can see the key has like a little thing in there. So I take the load and I divide it by the area. And what would be the units of that? Load is measured in force per squared length, which is area, which is meter squared. So newtons divided by meter squared is Pascal. It's the same unit as the yield strength is the same unit as the elastic modulus. Even though the elastic modulus is a slope, the strain has no units. There is Tabor, T-A-B-O-R, Tabor, relationship that states for an average metal, the hardness, H, is equal to 3 times the yield strength for a metal, 3 times the yield strength. And I can tell you that a hardness tester can be inexpensive, like my key and a little bit of weights, and it can be portable. That tensile machine is 50 grand to begin with, unless you buy mine, which is cheaper. But it can only do 20 kilograms of maximum force, so you can test some wires and stuff. But the big machine is not suited for testing wires and stuff. We can test human hair. The Pashmina fiber from India, we measured 15 microns hair from a special lamp. Anybody has a cashmere sweater? You know what cashmere is? What is cashmere? Made from? What about pashmina? Go to the store and try to buy it, see how much it is. Or go online. It's not fake, see how much it is. Okay, anyway, we're making this indentation. We know how much load was applied, but we're just putting dead weights, right? And then we use some sort of a measure to see how much this impression was. And there are different materials that are used for different ways of testing. The diamond is the hardest over here. Then we have nitride steel, cutting tools, hard file, some easy to machine steels, brasses and aluminum alloys, and most of the plastics. So this is the scale of increasing hardness. It's measured by using different indenters. And then there's Rockwell and superficial Rockwell, different scales. There's diamond cone and this different diameter steel spheres and the corresponding load. 60 kilograms, 100 kilograms, 150. And then there's superficial Rockwell of 15, 30, and 45. So all of this is very confusing, and unless you are in this business, I don't remember what those scales mean, because there's so many of them. You know, if I take a diamond and I apply 150 kilograms, I'm going to make a big hole, because this plastic is soft. What I can tell you is the universal hardness, which by definition is load divided by the indentation area. And that is measured in pascals. Range. And this was taught to me in a class like this. And what you need to understand is that, okay, you can always go back to those tables and the definition. And once in a while in a paper, I see HRC or some of those units. I mean, it's Rockwell hardness, Rockwell on the scale C. That's what it means. You can see there's a combination of, we have 6 different loads. And we got diamond, and we got 4 different diameters of the steel spheres. And the reason is because some materials are very soft and some materials are very hard. And we need to make an impression so that impression is left in there and remains. Okay. Another scale is Brinell hardness, and this one has a single scale, and it's denoted by HB, hardness Brinell. And it's a 10 millimeter sphere, either made from steel or tungsten carbide. And the load is between 0.5 ton to 3 tons in 0.5 ton increments. And this is the equation for the hardness. 2 times P divided by pi d times d minus square root of d squared minus small d squared, and d is the diameter of the ball, which is 10 millimeters, and we have d is the diameter of the impression that we're making. And there's a relationship between Brinell hardness and tensile strength, and again, I never bothered to memorize it because there are just way too many things to memorize. I'm not AI, I'm a human being. But you just need to understand the idea. And what's the definition of universal hardness? What do we measure? The load you apply. I mean, you can measure it, but you know how much you put in, how much load you put in. What is your input and what's your output? The area that is this impression. So we need to measure that somehow. Okay? And then we divide the load, the weights we put in newtons by the cross-sectional area, by the area, projected area is called. And that's the hardness. Now, as you can imagine, there are statistics that's involved. You know, if I flip a coin, if I'm not cheating, then it will be half tails, half heads, something like that. But whenever we're trying to measure something that's not exact, and that it's not exact for different reasons, it's the resolution of your measurement tool, it's the repeated measurement, it's the variability of the property in the material. It varies. We need to use some statistics. And one parameter is an average value. And you're familiar what an average value is. Average value on the last exam was 70.7 or 70%. In another class it was 49%, and they're not as happy as you are. So You understand the concept of the average. We take all of the grades, combine them, sum them, and divide it by the number of students. So you repeat the measurement, the same measurement, and you get slightly different answer every time, so slightly different number. You combine them all together, you sum them, and you divide it by the number of measurements. Right? That's average value. Now, we need to, okay, so that's what it means mathematically. Sum of all the values divided by their number. The second parameter is called standard deviation. And standard deviation, sometimes people plot it as error bars. So here's your average value and the standard deviation. Now standard deviation assumes that there's bell curve distribution, Gaussian distribution. It's not always the case, but here's a formula for the standard deviation. And if you use Excel, it's stdev. stdev and your data, and it's going to calculate it for you. There's another parameter that's called standard error. And what I want you to do, just for your own benefit, is get some data. You can generate your data 1 through 5, and then you can calculate the standard deviation in Excel and standard error. And one is going to be larger than the other. And as long as you say this is standard deviation, or this is standard error, as long as you disclose it, it's okay. But sometimes you want to show things a little better than what they actually are. You have any questions about this? Have you seen this before? Have you taken statistics? ANOVA? When I was a grad student, I took a 3000 level statistics course, a whole bunch of undergrads from biology. I had my ass whipped. I barely got a B because I would make a stupid mistake without paying attention to the details. And it was a 3000 level course, and I was a graduate student. I was embarrassed to get a B. But anyway, it's okay. I'm here. Still here. A friend of mine that we're playing with the eye, he created a series of books. It's called The Dog You Chose. And those books are on Amazon. He wrote 100 of them. There are 409 breeds in the United States. And then there's a song for each one of those books. There's a dog breed called Otter Hound. And that breed was created to get the otters. So if you get that kind of dog, it's going to dig up your backyard like crazy. So, and the song he wrote is still here. So the dog breed is still here, although the humans are not using it for hunting otters. Safety factor. What is a safety factor? A factor of safety. What's the idea? Yes.
Like the degree of which you want the force failure. So it's the force that is allowed over a factor that you want it to not fail at. Like if you want it to not fail at, I don't know. I forgot like how to explain it.
All right. Let's explain it together. Look at this. I take this rubber band, and I keep loading it. And at a certain point, it's going to snap. I'm not going to do it. I may get hurt on my job. So, if I'm not exceeding that load, then it's not going to fail, correct? So the safety factor is this number n. which is the stress level that the part is going to see compared to the yield strength. So we're never actually reaching yield strength. And you can see based on this, it has to be greater than 1, and it varies from roughly 1.2 to 4. Now 4 would be huge over design. So if you apply a safety factor of 4 to, let's say, a vehicle, the gas mileage would be horrible because it would be way over designed. And then if you are designing something that is only working for a short period of time, like something for a plane or a rocket or something like this, you can push it closer because it may be 1/10. Okay, let's do a problem. A cylindrical rod needs to be constructed from the steel that has a yield strength of 310 megapascals. It needs to withstand a load of 220,000 newtons without yielding. Assuming the safety factor of 4, specify the suitable bar diameter. And the stress is equal to the load divided by the area. The area of a cylinder with diameter d is pi d squared over 4, or pi times d over 2 squared, where this comes from the area of a circle, which is pi r squared, and r is d over 2. When it's squared, it becomes pi d squared over 4. And I have statistical data that half of the students at an undergrad level don't know this, which is fine. I'll teach you anyway. Okay, and then we have the factor of safety of 4. The yield strength is 310 megapascals. The load is this, and we can calculate the diameter of 60 millimeters. And I expect you to be able to solve a problem like this. Okay, mechanical force that's applied that's converted into stress. The degree of deformation is normalized to strain, stress strain. There's elastic deformation, which is not permanent. That's when the stress strain relationship is linear. Plastic deformation is permanent, and the stress strain behavior is nonlinear. And the stiffness is a measure of the resistance of material to elastic deformation. The strength is the material resistance to plastic deformation. And ductility is the amount of plastic deformation at failure. There are two ways to measure it, either percent reduction of elongation or area. Yes? We're going to see a lot of failures as examples, but as far as the theory of failures, explicitly they're covered in mechanics of materials course. So yes and no, not to that extent. Okay, and the hardness is the resistance to localized surface deformation, Rockwell and Grinnell hardness. Okay, we are going to jump into the next chapter and discuss how to make things stronger. And to do that, we will consider metals. So we're going to be taking a look at dislocations. And how those properties are affected by the dislocation mobility. And also processing techniques to make things perform better. And see how heat treatment may help. Plastic deformation happens by the motion of dislocations, and this process is called slip. And the reason it is called slip is because we have this extra half a plane, and the dislocation is denoted by the inverse letter T, like this. The reason is because there's half a plane of atoms and there's another plane. So this plane on the bottom, this plane here, is called a slip plane. It's the plane upon which that half a plane is moving. So here's a plane and it moves like this. And it happens due to shear. We apply shear, as a result, this dislocation moves. And you can see that eventually it can come up at the surface. And there are different analogies. Caterpillar movement or moving this carpet. It is doing certain things at a small scale and a small distance. Because otherwise the energy to do that would be very large. And this is the mechanism to minimize the energy for the process of plastic deformation. Believe it or not, the first dislocations, I think they're called Somigliana and Volterra dislocations, were predicted by mathematicians. It's the movement of extra half a plane of atoms by breaking and reforming interatomic bonds. So here you can see it has to jump from here to here. That's how it physically moves. So it's extra half a plane that's moving. And there are two types of dislocations. There's edge and there's screw. And for the edge, you can think of it when the whole thing is displaced. For the screw, it's like this, so portion of it. In the end, the result is the same for both screw and edge dislocation. The step on one side of the surface ends up on the other side for a single crystal. Why does it work? It has to do with bonding for metals. And for metal, we have the electron cloud. So those electrons in metals are shared between many different atoms. They're free electrons. That's why metals are conductors of electricity. And here's some examples of copper, aluminum, or iron. And the dislocation motion in metals is very easy because bonding in metals is non-directional. What does that mean? Non-directional bonding. It's the same in all directions. And because they're close-packed planes, and also directions for slip. How many of you have ever tried to jump on a tattoo? You can jump really high if you are in sync. But the first time, imagine I'm standing on a huge piece of rubber. I will not be able to jump as high. So the same goes with atoms. When the atoms are close packed, they are stiffer. If they're more spread apart, it's kind of like trying to jump on your mattress. You're not jumping as high. Close packed planes and directions for slip. In ceramics are covalently bonded. Or they are ionically bonded, which could be a combination of both. It's very difficult to have dislocations. Why? Because the bonding is very, very strong. And if there is ionic bonding, what does that mean for an ionic solid? For every plus, there has to be a minus, so it's neutral overall. And to move things around, it's going to be much harder. Okay, let's define a slip system. Slip system is a combination of a plane, actually half a plane of atoms, and a slip direction. Slip plane is a crystallographic plane on which slip occurs most easily. with highest planar densities. Remember we calculated the planar density? This is the reason why. We calculated the planar density to know which are those planes where the dislocations can move. And the slip direction is the crystallographic direction along which the slip occurs most easily. And those are the directions with high linear density. Why? Because if atoms are touching like this, there's a direct transfer. If the atoms are touching like this, you're taking a projection at 45 degrees most likely. So slip system consists of a slip plane and a slip direction. And those Miller indices and directions come in handy. So for FCC, the slip system is 111 plane or family of 111 planes and family of 110 directions. This is the 111 plane. And this is the 110 direction. And so is this, and so is that. This is a planar view for FCC. And this is very important because you can see that there's more than one plane like this. You can actually calculate how many planes are like that. And each one of those planes would have 3 directions. So you can do the math. That for FCC, there are going to be 12 slip systems. Here comes the answer to somebody's question earlier. Except that here, we're linking it to the crystallographic orientation of the material, of the single crystal. You see here's the force F. If we take an arbitrary plane that's positioned at 2 angles with respect to the axis. One is the angle between the axis of your sample and the normal to the plane. And that we call angle phi. And the other one is going to be the slip direction, and we're going to call it the angle lambda. It's one angle more than the mechanics of solids because mechanics of solids deals with homogeneous material. And here we're linking it to the atomic directions and atomic planes. So the shear stress, or what is called resolved shear stress, tau sub r is equal to the F prime divided by A prime. F is this force, and F prime is this force, and A prime is this area. In mechanics, it's actually called area vector. And this is called resolved shear stress because this stress is resolved by the fact that you applying the force in this direction. This force is going to have a projection on a certain plane that is not, that is a certain angle with the axis of the applied load. And then the result shear stress depends on the orientation of the normal slip plane and the slip direction. So we can write that F prime from trigonometry is equal to the F, microscopically applied load, times cosine lambda. And then we can write the same equation for the A prime, which is equal to the A divided by cosine phi. Does this make any sense to you? Yes? So the difference in material science that deals with critical result shear stress compared to mechanics is that in mechanics there is only one angle, but here we have 2 angles because it has to do with the slip direction. Okay? In mechanics, it would be this force. And that's the difference. Okay, what will cause the slip? And let's derive this equation for the critical result shear stress. We write that tau sub r is equal to the F prime divided by A prime, or F cosine lambda divided by A divided by cosine phi. This becomes F over A cosine lambda cosine phi. And that's equal sigma, the normal stress, cosine lambda cosine phi.
Would that be in degrees or radiant on that one?
I'm sorry, what?
Would that be in degrees or radiant for the cosine?
It doesn't matter because the cosine or sine are the same regardless of how you express the angle, right?
No.
What is the sine of 30 degrees? One half. Does everybody know that? No, because I have statistical data for 20 plus years that half of the students are not going to switch their calculator from radians to degrees, and they'll give an answer of 30 radians. What is the sine of pi over 6? One half. Did we do the Excel trick yet? Does anybody have their computer on them handy? Open up Excel. I'm going to be saving some lives of the future generations. Open Excel and say equal SIN and then brackets 30. What do you think she's going to get? The angles in Excel, by definition, are in radians. So the answer is going to be minus 0.9. You tell me you're supposed to check AI. How about Excel? You need to check Excel to make sure that the answer you're going to get is what you are expecting to get. Because we always trust the computer. My computer must be right. Yes? Okay. Who knew that the angle in Excel is expressed in radians? And how did you know? What? Physics 1 lab. And the rest of you didn't have that lab. So, did you have that lab too? I'll see you Thursday.